So now that we have our trick of doing implicit differentiation, which was based on our trick of the chain rule, I want to put this idea to work. So let's consider an inverse function. Now, that's a really weird idea. Wait a second. What's it mean to be an inverse function? If I say that I have an inverse function, like there's an inverse for x squared, what's the inverse? What undoes x squared? A square root of x. So when I write something like this, it's really the same as saying that I can write x as f of y. Now, why would I bother with such a crazy sort of kind of inside-out definition? Well, let's consider the function ln of x. I don't know how to take the derivative of this. And that's my problem. I want to know how to take the derivative of some new functions. But the logarithm is an inverse function. What is the logarithm the inverse of? If I wanted to do this rewrite, what would I use here? Is it E? It is E. So what I would end up rewriting is that e to the y is equal to x. Now, I don't know how to take the derivative of the logarithm, but I do know how to take the derivative of an exponential. So if I think of that right-hand equation as representing the same y here, I can take the derivative this way. If I use yesterday's trick of implicit derivatives and using the chain rule on that e term. So if I now use implicit derivatives here, what do I get? Well, let's start on the right side. I'm taking my derivative in x. What's the derivative of x? 1. Great. What's the derivative of e to the y? Remember, I'm taking my derivative in x. Ooh. What does that mean? Almost. It's not e to the y prime. Right, I leave the y alone. I take the derivative like it was e to the stuff. The derivative of e to the stuff is e to the stuff, and then I hear in my bad infomercial voice, but wait, there's more. And that's where the y prime comes into play. Oh, wait a minute, right there. My goal is to get y prime. Y prime is 1 over e to the y. I did it. I found dy dx. But I'm not happy with this result. Because over there on the left, I have an explicit function. I really would like to have an explicit derivative. When I take the derivative of x squared, I get 2x. It's still in terms of x. I want to take the derivative of ln of x. I don't want to write it as 1 over e to the y. Those don't even look like they go together. So how can I fix this final result to turn it into x's? That's an e to the y, right? That's an x. It says so right here. Wherever I have e to the y, that's the same as x. I have an explicit. I can now just write this as if it's a rule. Whenever I have an ln of x and I take the derivative, I get 1 over x. Independent of how I got it, I now know that works. Whoa. By the way, this somehow is really, to me, very interesting because I just took a function that has nothing to do with powers of x, but its derivative is x to the minus 1 power. There's somewhere hiding from me, behind the curtain that I can't see through yet, there's a connection between logarithms and e and powers of x. I don't know what it is yet. So I just added a new rule to the things I want to remember. That way I don't have to go through this crap every time. Now I've got the power rule, I've got the product rule, the quotient rule, the chain rule. I've got my trig functions which get given to me. And now I've got this. But science people don't work in ln all the time. If you're in a lab and you're working in pH or in molar concentrations, what exponent base are you using most of the time? Base 10. This is base E. ln is base E. If I'm in computer science, instead of working in base 10, that's a really bad 10, maybe I'll be working in the logarithm base 2 because I want to work in binary. Maybe I'm just working in some weird base. There's an entire set of applications in number 3 that work in base 3. I don't know why. But I could be working in any base, B. As long as B isn't 1 and B is a positive number, I can work in any base. When we were doing the chain rule last Friday on our recording, I said this comes up in powers all the time, right? We were able to change powers. If I had something that wasn't e to the x, but maybe it was 5 to the x or 10 to the x, I made a way to change powers, right? I can do the same thing here. If I'm in any base, I can always rewrite that in ln's. Because it turns out that the log base b is the ln of x divided by the ln of the base. But the base is a constant. If I'm working in base 10, I'll write that as ln of x over ln of 10. You've got a calculator. What's ln of 10? Some crazy number, right? But it's a number. So I could think of this as 1 over that number times ln of x. I separate the number from the fraction. which makes this a coefficient, doesn't it? Like it was a 5 or a 2 or a 17. And when you take the derivative of number times function, what do you do with the number? The derivative of number times function is so if I want the derivative of log base 10 of x, I'm going to treat it like this. And I'm just going to leave this number alone. What's the derivative of ln of x? 1 over x. There's nothing special about the 10 in that problem. This works for any base you want. The derivative of the log base b of x is 1 over ln of b times 1 over x. Because that's what our change of base formula allows us to do. 99.99% of the time, if I'm working with a logarithm, I'm working in base e. But that's because I'm a math geek. If I'm in a lab, most of the time I'm working in base 10. Or I'm converting it so that I can work in base e to make my life easier in the computations I'm working in. This is particularly useful in places where we do catalytic reactions and we're looking for reaction speed changes, or we're looking for rate of dissolution or rate of osmosis or any of those sorts of changes in concentrations. A lot of titration problems do this. So most of the rest of what I'm going to do today is in base E. But this means I can put this with all of my other rules as well. This is ln of stuff, not ln of x. And if it's ln of stuff, I hear a little rattling in the back of my head. That's not my brain rattling around, although on some days it could be. What is that little rattle in the back of my head doing? How? Unfortunately, no, logarithms don't separate like that. The ln of a sum is not the sum of an ln. There were properties of logarithms, but adding wasn't one of them, unfortunately. No, that little rattle that I'm hearing in the back of my head, that's the rattle of those nesting dolls. This is ln of stuff, not ln of x. I'm going to treat it like the chain rule. The derivative of ln of x is 1 over x. So the derivative of ln of stuff is 1 over stuff. But wait, there's more. What goes in that set of parentheses? The derivative of the stuff, which in this case is a 3x squared. Now, do it again for me. The derivative of the ln of the square root of x. What do you get?
1 over x to 1/2. We have x to the -1.
1 over stuff, derivative of the stuff. Yes? However, I'm going to do something that we didn't do in the previous part. I'm going to do the simplifying. A negative power means it goes where? On the bottom. So this is 1 over x to the 1/2, and then a 1/2, and then this is also 1 over x to the 1/2, which means all of those are on the bottom, aren't they? I have an x to the 1/2 on the bottom, I have another x to the 1/2 on the bottom. What do I get on the bottom? What do I do with those powers? Since we're multiplying here, say again, I add the powers. But x to the 1/2 plus x to the 1/2, sorry, x to the 1/2 plus 1/2, that's just x to the 1. And something raised to the first power is just that thing. This is a lot nicer than that, isn't it? But when I see 1 over x, my brain says if I had 1 over x, it really should have come from ln of x. So now, Jack, you tried to use a property of logarithms. So now I need to remember properties of logarithms. There were 3 main properties of logarithms based on our properties for exponents. And Dean, you just said if I'm multiplying the two things that have the same base, I add the powers, right? A logarithm is asking me what power I'm using. So if I was saying I want to know what power goes where I multiply things, that's adding the powers. Jack, this was what I think you were getting at, but it only works when the inside is multiplied to separate them to be adding. I can't do it when the inside is adding itself. Same thing works with dividing. If I'm dividing, what do I do when I'm taking like x cubed divided by x squared? What do I do to the powers? So I'm going to turn this into subtraction. And here's the kick one. What happens when you have a power of a power? We did this in the discussion of the chain rule last Friday. X squared cubed. What do I do with those two powers? Because I multiply the powers, right? So I'm going to turn this into multiplying my powers. Exactly. Hey, wait a second. Let's look at that last one again. Here. Square root is a power, isn't it? The derivative of ln of the square root of x is really the derivative of the ln of x to the 1/2. And now by this rule right here, rule 3, I can take that 1/2 power and put it out front. Perfect. If it's in front here, Dean, what do I get to do with that 1/2 there? I get to take it out front. And then I just need the derivative of ln of x. And the derivative of ln of x is 1 over x. Lo and behold, 1/2 1 over x. 1/2 1 over x. I like this, being able to take apart things because they have powers and multiplying and dividing in them by using an ln. This is really convenient because it prevents me from having to do really gross chain rule work. For example, and I know this one is deliberately kind of crappy. Let's take the derivative of ln of x plus 1 over the square root of x minus 2. Now, I don't know what psycho came up with this. I stole it out of the textbook. But if I want to use the chain rule, I'm going to say, oh, it's derivative of ln of stuff. So what I'm going to do is I'm going to take 1 over stuff. But wait, there's more. And here's where things start to go to hell in a handbasket. Because if I want to take the derivative of the stuff, I need the quotient rule, right? But look at the bottom of that quotient. The bottom is not square root of x. It's square root of the quantity x minus 2. So that quotient rule has a chain rule inside it. Blah. I don't want to do that. That's nasty, that's gross, that's disgusting. So how do I avoid doing that? I get to use my 3 rules to figure out how to take apart this logarithm to make it simpler. So I'm dividing, right? There's division here. And division becomes subtraction. ln of the top thing minus ln of the bottom thing. But the bottom thing's got a root. Root becomes a power, and powers go out front. So 2 steps. One to rewrite it as power, and one to pull that power out front. If I want the derivative of this, I could just as easily take the derivative of this. Now, why is this better? These are chain rules, right? ln of stuff, ln of stuff. What's the derivative of x plus 1? And the derivative of x minus 2? So the chain rules are a crap ton easier, aren't they? So if I do the derivative of ln of this complicated expression, instead, by doing this derivative, well, then my chain rules just got a bunch easier. This is 1 over x plus 1 times the derivative of the stuff, 1, minus 1/2, 1 over the stuff times the derivative of the stuff. That's not a little bit easier. That's a whole lot easier. However, to do this, I needed to use my properties of logarithms a lot. Questions? I mean, if you really want to, we can do it the other way. It's just disgusting. Questions?
Do this up by line.
Yeah, I'd leave it just like that and walk away. If you really wanted to, you could combine the fractions. I'm not sure it's worth it. Common denominator and all that junk, I wouldn't do it. What other inverse functions do you know that you were taught in other classes before this? Oh, hang on a second. Wait, I forgot something. I'd like to make a note. If I think about ln of x, what's the domain of this function? What numbers are allowed into an ln? What numbers are not allowed? Algebra was a long time ago, man. If you draw the graph, it helps. Or it might trigger something that you will remember using the graph. That's the graph of ln of x. Yeah, the things have to be positive. Yes? There's a vertical asymptote at 0. Nothing's on the right side of this picture at all. Sorry, the left side of this picture at all. I'm stuck. There's no graph over here. But the derivative is 1 over x. And 1 over x works both for x positive and for x negative. Huh. And the graph of 1 over x looks like this, right? Which means they almost look like they're symmetric. It turns out that that symmetry is not an accident. And Dean, the fact that I can only use positive things inside an ln makes me think that I should restrict myself to positive things. But there's another way to restrict myself to positive things. I can think of the absolute value. Doesn't that make everything positive except for 0? Well, that would take this picture and it would reflect it over there. ln of the absolute value of x is going to look like that. And this side goes with 1 over x like this, right? Think about a tangent line on this. The tangent line going to have a slope that's positive. When it's close to 0, it's going to be a big positive. When it's further away from 0, it's going to be a small positive. Big positive, small positive. I like this. Now think about tangent lines over here. Tangent lines on this side are going down. Slopes that go down are, and when they're over here, they're small negatives. And when they're over here, they're big negatives. I can even go so far as to think of this as if it was a piecewise function. And then I can use the chain rule. Guess what? The derivative of the ln of the absolute value of x is still 1 over x. It works the same on both sides. Oh, that's sneaky. Why would I bother to do this? Two reasons. One is to address that mismatch in the domain. If ln only works on the right, my derivative should only work on the right, but my derivative works on the right and the left, so I really want a function that works on the left as well. And the other reason is something we'll see at the end of chapter 4. I want this to be as general as possible, and that's what this helps me do. Questions? All right, then with that in mind, let me go back to the question I was asking a moment ago before I forgot that I'd not done this. What other inverse functions have you seen in other courses? Because it's not just ln or logarithm in whatever base. There are more. Hint, there are buttons on your calculator. Trig function. I've got sine inverse and cosine inverse and tangent inverse right on my calculator. And if I have those, then there's also a secant inverse and a cosecant inverse and a cotangent inverse. I will tell you with some moderate sincerity that I very rarely use these latter three. Almost always, if I'm using an inverse trig function, I'm using one of the top three. But I will go so far as to tell you that I rarely write this notation. I don't like that inverse -1 power thing. Because I keep seeing a negative power should be on the bottom. That's not what this is. So I tend to write arc sine and arc cosine and arc tangent. Now, the reason for that is because an angle in radians is a measure of part of an arc of a circle. And this, you give me the sine, I give you an angle. If I'm giving you an angle, I'm giving you an arc. So those are actually the older symbols for those three functions. We'd have arc secant and arc cosecant and arc cotangent as well. But that's just a notational convention. Different books will write them differently. Different online resources will write them differently. Pick one. Sine, cosine, or tangent? Sine. I would like to answer the question, what is the derivative of the inverse sine? And again, I will say with complete assurance, I don't know how to do that. Well, what am I supposed to do now? I'm going to do the same thing we did for ln of x. Because if I think about the inverse sign, y equals sine inverse of x, that's the same as what other equation? Using the inverse idea. And there's an implicit equation. It's implicit, so I can use the implicit derivatives. Yay, I know what to do. One of the most common things people in math do is they take a problem they don't know how to do and transform it into a problem they do know how to do. Old bad joke. An engineer, a physicist, and a mathematician check into a hotel late at night and go to 3 rooms that share a corner. So picture the rooms in an L shape, the corner between them. They all plug their stuff into the plugs, which happen to go into that corner, and it overloads the circuit and catches fire in the middle of the night. The engineer wakes up, sees part of his room on fire, grabs the trash can, runs into the shower, fills the trash can with water, and lays down to sleep in a soggy bed. The physicist sees the fire, sees the trash can, goes into the bathroom, measures a particular amount of water into the trash can, goes to sleep in a dry bell. The mathematician sees the fire, sees the trash can, sees the shower head, goes, I know how to solve that, and goes back to sleep. I know how to solve that. I'm basically done. Take the derivative here. How do I take this derivative? Using my implicit rules. What's the derivative of x? What's the derivative of the sine of y? But wait, there's more. Because I'm taking my derivatives in x. So what's the extra piece I need on the end here? Bingo. And that means that y prime is 1 over cosine of y. I'm done. I can see your expression too going, no, you're not. No, you're not. You're going to with me. I'm not done. I know I'm not done because you're mean that way. Well, yes, just like with before. I'd rather have this written in terms of x. But I don't have anything anywhere up there that says, how to swap y for x easily, right? But this is a trig function, right? So if I think of this, I got to ask you to go back to your trigonometry in your pre-calculus class. When you were figuring out sines and cosines, you had circles and arcs, but you also had triangles, right? So if I were to take this expression right here and put it on a triangle, sine of y means that y is an angle in that triangle, which makes sense because that's the arc I get out of the arc sine. So I would draw a little right triangle. And I would have y right here. Which 2 sides of my triangle are involved in sine? There's a little mnemonic we had to remember. Remember sine in the triangle and cosine in the triangle and tangent in the triangle, and which sides went with what? Which sides go with sine? Opposite and hypotenuse. SOHCAHTOA. So opposite and hypotenuse. But the sine is equal to x, right? I want a fraction. I want opposite over hypotenuse. I can write x as if it was x over 1. So I'll put opposite and hypotenuse. Just like I was on the unit circle, the radius is 1. Oh, I like that. I like that. Trig question. I'm going to use cosine. And we just rattled off the little mnemonic. For cosine, I need adjacent and hypotenuse. The adjacent is the side I don't have. What is the length of this horizontal side in terms of 1 and x? How the hell am I supposed to find the third side of this triangle? My favorite Greek geek. Every time we do a right triangle, we use the same person's name over and over and over and over again. Who's the person that tells me about sides of right triangles? I'm going to send you all over to Lynch Hall to look at my office door because my parents visited Greece this past summer and bought me a t-shirt which has this result on it in Greek. I don't read Greek, but I know this theorem like the back of my hand. Whose theorem is for right triangles? My buddy Pythagoras. This squared plus this squared is equal to this squared. So if I want to find this side, I know question mark squared plus x squared is equal to 1 squared. But 1 squared is just 1. So question mark squared is 1 minus x squared, which means the length of that side is the square root of 1 minus x squared. Now, why do I give a flying about that? Because I want cosine of y. And now I know all 3 sides of this triangle. According to this triangle, cosine of y is adjacent over hypotenuse. And if I put that in here, I get, when y equals the inverse sine of x, I get y prime is 1 over the square root of 1 minus x squared. And just like before, Jordan, now I have an explicit formula for an explicit derivative. I solved it implicitly. And then I went back to the triangle to rewrite it so it could become explicit. I can do all 6 of them this way. The derivative of tangent is secant squared. So if I have tangent of y, I'll have secant squared y times y. I can do the whole thing for the inverse tangent or the inverse. I don't want to go through all of this crap. Remember I told you you didn't have to memorize the trig functions? You don't have to memorize the inverse ones either. They'll be on the formula sheet attached to the exam. There they are. Again, this now means these can become part of my other formulas. So I can use the chain rule. I can use the product rule or the quotient rule involving inverse trig functions. Those work with me now. Things like, these are also in the textbook, excuse me, before I wander off to try and do something else. These are on page 223. Here is a function. I want you to take its derivative. I'm going to need two different rules on top of that list on page 223. Because I don't have the arctangent memorized and I've only shown it to you once. So if you've got your textbooks with you, turn to page 223. If not, grab your Canvas page where this formula sheet is. We're doing the inverse tangent. You can just write it down right off of here for the moment. Inverse tangent, right there. The derivative is 1 over 1 plus x squared. So I'll make a note off to the side that says the derivative of the inverse tangent is 1 over 1 plus x squared. Every time I see an inverse trig function or a trig function, I know I'm going to need something off that page. You probably should download and or print that out so you get used to looking at it and you know where things are on it and what things are on it and what things aren't. Because in addition to needing that, I also need the product rule because I've got an x over there on the left. X times arctangent, so I need a product. But wait, it's even worse. It's not arctangent of x. It's arctangent of the square root of x. What does that mean I need to do with the square root thingy? Say again? Yes, but because it's inside something else, chain rule. And that's where I'll use the power rule. So that's all when I do the derivative of the second part, right? So the product rule says I do the derivative of the first part, leave the second part alone. Then add, leave the first part alone. Do the derivative of the second part. Okay, people, here we go. The derivative of the arctangent of stuff is 1 over 1 plus stuff squared. But wait, there's more. And here's where my chain rule shows up. And Chase now is where I use that power rule. The derivative of the square root of x is 1/2 x to the negative 1/2. And Jack, if all I'm asked to do is find the derivative, this is my final answer. But I know that the textbook's not going to leave stuff like this. If I go look at the answer for this problem in the back of the book, they're going to do all the simplifying over there, which is just pissing me off. But it's not as bad as you might think it is. There's nothing I really need to do that part. But over here, the x is on the top because it's x over 1. What happens when you square a square root? So this becomes 1 over 1 plus x. Then there's a 1/2, What happens with that negative power? It goes on the bottom. Now, this x is on top, this x is on bottom, and these are being multiplied. That means this x is divided by this x to the 1/2. When I'm dividing, what do I do with the powers? So this becomes x to the 1/2 over 1 plus x times 2. That is actually the answer written in the back of our textbook. Except they don't write a 1/2 power. What do they write instead of a 1/2 power? A square root. Ta-da! Trig functions have inverses. Hyperbolic functions have inverses. You probably didn't do hyperbolic functions in your pre-calc class. They're more often just written in terms of e, but occasionally you'll see hyperbolic and inverse hyperbolic functions as well. Exponents inverses are logarithms. Power functions inverses are roots. So inverse functions show up a lot. Questions? All right. In my chain rule work, at the end of that chain rule discussion, I put up a huge ass example. It was like 9 layers deep, right? And stuck in the middle of that was a weird function. Again, I don't know how to take the derivative of this. I don't. If it was x to a number, I'd use the power rule. If it was number to the x, that would be an exponential. E to the x, 3 to the x, 10 to the x. I could do those. Just the x is in both places. That's enough to just be really annoying. So I need to fix that. One of our rules for dealing with logarithms allowed me to move exponents to become multiplication. So just like once we learned how to do implicit derivatives, we were able to do these ideas. Now that I have the derivative for a logarithm, I can use logarithms to make my life easier. This process is called logarithmic differentiation. Or logarithmic derivatives. Just like we had implicit derivatives, where we used the chain rule to do something new, I now have a new derivative where I'm going to use the logarithm to do something new. And the first thing I do is I put in ln on both sides. Now, on the left side, I have an implicit expression because it's ln of y. But on the right side, I have logarithm of stuff in x. There's a power inside a logarithm. What can I do with that power? I can bring it to the front. And that leaves on the inside just an x. Hey, wait a minute. This right-hand side is a product. If I want to take the derivative now, take the derivative on the left and the derivative on the right, I know how to do that now. On the right, I use the product rule. Derivative of the first part, leave the second part alone, plus leave the first part alone, take the derivative of the second part. What about on the left side? Derivative of ln of stuff. But wait, there's more. What goes here? A y prime. Since my goal is to figure out what y prime is, I just have to move the y to the other side. Y prime is y times this stuff. Wait a minute. 1 times ln of x is just ln of x. What's x times 1 over x? Just 1. Now, implicit derivatives had y's and x's mixed together, yes? But I know what y is supposed to be, so I'm just going to plug that right back in here. I'm going to write that as x to the x times ln of x plus 1. And there's an explicit formula for an explicit derivative. Using my properties of logarithms makes my life easier. Even when I'm dealing with functions that don't have any sort of crap like this going on in them, but they're just complicated looking expressions. This one is just designed to be annoying. Again, I say to you, it's a fourth power. I could turn it into a 1/4, sorry, it's a fourth root. I could turn it into 1/4 power, right? I could do this with nothing but the power rule and the chain rule, yes? But the chain rule is going to be disgusting because that's a quotient rule with ugly stuff in it. But if I took an ln, I wouldn't need to do the power rule at all. And I could convert this to something easier. What do I do with the fourth root? Because it'll become a power, right? It'll be a 1/4 power, and powers go out front. Wait a minute. Now I'm dividing. When you have an ln and you're dividing, what happens? So this is going to be 1/4 parentheses ln of x squared plus 1 minus ln of x squared minus 1. If I want to take the derivative on the right, those are chain rules. The derivative of ln of x squared plus 1. What's the derivative of ln of x squared plus 1? ln of stuff.
One over x squared plus one.
Exactly. 1 over stuff, chain rule. And then here, 1 over stuff, chain rule. My goal was to get y prime alone. Y prime equals, I'm going to put a y over there, but this is y. So I get 4th root of x squared plus 1 over x squared minus 1 times 1/4 parentheses 2x over x squared plus 1 minus 2x over x squared minus 1. Rather than do the quotient rule, the chain rule, and a whole bunch of simplifying, I like this better. But it requires me to remember to use the logarithms. If I did it the long way, it works. I don't think this is better, especially because of that negative 3/4 power. That's just, ooh, unpleasant. And the result is something with negative 3/4 powers in a lot of weird ways. I don't like this. This at least looks a little nicer. Questions? So we have now done derivative after derivative after derivative after derivative in lots of different ways. I'd like to put these to use. As I said earlier, sometimes my derivatives represent catalysis, osmosis, reaction rate. There's a lot of things I can use a derivative for. Tomorrow, we're going to look at several of those different scenarios and see what sort of ways we can put our derivatives to use. So I hope you have a wonderful rest of your day. I will see you tomorrow.